Well, at the risk of putting some of you to sleep, I want to do a computation with you. And I want to do it with you because it's so fun and surprising, some things that happen. So we're interested in the length of A cross B. That's what I want to study. But to help me understand that and to keep the computation less nasty, if you think about it, the length here involves a radical, and I can just square it. I'm going to consider the length squared, and then at the end I can square root and recover what I want. So let's think about the formula for A cross B. We've got that written down. Go back to your notes if you want to. And then when you take the length squared, you're just getting rid of that square root. So it's each component of the cross product squared, component squared, plus component squared, plus component squared, and then usually you'd have a square root, but we get rid of the square root because of this square. And so the point is, when you compute this, you end up with the following. You have, remember this length is going to kick out a scalar, so this is a scalar now. I have the first component, A2B3 minus A3B2 squared, plus the second component, and there's a negative there, but the negative goes away, so I'm going to write this as A1B3 minus A3B1 squared. I'm going to be tight on space. I can see that already. We'll slide that over. And let's slide all of this over. There we go. Maybe we can squeeze it in. And the last one, the last component is going to be A1B2 minus A2B1 squared. Okay, so far so good. So now I won't do all the details, but I want you to go ahead and imagine at least squaring each one of these out. Yeah, it's a little bit messy, but when you do that, you're going to get the following. Let's write it down. You're going to get A2 squared, B3 squared. Then you're going to get a minus 2A2, A3, B2, B3. Oh, yes. And then you're going to get a plus A3 squared, B2 squared, plus A3 squared, B1 squared, minus 2A1, A3, B1, B3. I'm just literally squaring each one of these. Plus, I need to drop down another line, A1 squared, B3 squared, plus A1 squared, B2 squared, last one now, minus 2A1, A2, B1, B2, plus A2 squared, B1 squared. So I didn't think through the foiling of each piece out, but when you foil them out, this goes with this one, this goes with this one, and then this one goes with the last one. So I just foiled them out. And now if you do some factoring and some grouping, I'm not going to work through all this. This is where the magic happens, but you end up with the following. So you're just doing algebra. You're factoring, you get A1 squared plus A2 squared plus A3 squared times a B1 squared plus a B2 squared plus a B3 squared minus an A1 B1 plus A2 B2 plus A3 B3 all squared. And these are one of those moments when if you were working this out by yourself, just doodling and playing and trying to figure out if you could clean this up. This is one of those moments when hopefully you realize something significant is happening here. This is just too nice to not mean something. And so let's pick it up here. What is this? A1 squared plus A2 squared plus A3 squared. Well, if I threw a square root on that, you would say that is the length of A, and this is length of B. So this, as it stands, is length of A squared. Let's clean it up. This is length of A squared. The next part is length of B squared. And then what is this? This is exactly A dot B, right? This is the dot product between the vectors A and B. A1, B1 plus A2, B2 plus A3, B3. So I get a minus A dot B all squared. All right. Let's use our other fancy formula for the dot product. So I get length of A squared, length of B squared minus And then I get what? Length of A squared, length of B squared, and then I get cosine theta, and it's squared because everything is squared here. Really, if you wanted, let's get rid of the squares, and let's say it's all squared. And then we'll write it again and push it in just to be crystal clear. So now we're here, and now we can get rid of the square on the outside, and we can say, all right, that's a square, cosine squared theta. And so now I realize, look, I can actually pull an length A squared, length B squared out. They're both both terms have length A squared, length B squared. So I can write this, man, that was hard for me to say, as length A squared, length B squared times 1 minus cosine squared theta. Hopefully you recognize that as a trig formula that you know. This is exactly length A squared, length B squared times sine squared theta. All right, whoa, that's crazy. So what have we actually come up with? We've shown that the length of A cross B squared is just the length of A squared times the length of B squared times sine squared theta. And now I want you to realize that our angle between our vectors we can assume is no more than 180 degrees. And so we know that sine theta is greater than or equal to 0 whenever my theta is between 0 and pi. And so that means that I can square root everything safely here. And so the point is, here is our key fact that we just discovered together. Great job, by the way. The length of A cross B is the length of A, length of B, times the sine of theta. Now, aside from being eerily familiar, we learned that not the length of the dot product, but the dot product itself, the dot product of A and B, is length A, length B, cosine theta. The length of the cross product is length A, length B, sine theta. That's really interesting that it works out that way. But there's a lot of questions, like what does this mean? How can we use this? Is there any other significance to this? So let me end the video here so that these don't get too long. In the next video, we'll learn 2 interesting facts that follow from this result.